Good day. Today we continue with our lectures in analog and mixed signal processing systems. And then we will, before we continue, we will very quickly repeat one most important thing, and this is the transfer functions of the RC networks. So if we look at one example of RC network like this, we would like to very quickly demonstrate how its transfer function looks like. So this is typical RC network, and what is interesting to us to see what is the character of this network. So let's say to properly bias the input signal to this, not bias, to give input signal to this RC network, we have to use ideal voltage source at the input, and then we have to monitor voltage at the output. We will call this voltage V2, and we can call this input voltage V3, and then we'll try to find transfer function. Let us, this is for the beginning today, let us call the nodes, for example, node 3, node 2, and this one here, which is a reference node or which is grounded, let it be node 1. Of course, here is open circuit. That means no current flows, here. I2 is equal to 0. So this is then without network without load, and at the input, as I told, is ideal voltage source. Okay, how we can find transfer function of this network? Usually we call the transfer function like this: T2, let's say V2 over V3, it will be T2 This is usual notation, but we will use different notation. Very quickly we will see what we want to say. We can call it T32. This is V2 over V3, the same. In our case, and then this means that the signal is going from point 3 to point 2. So that's why we use this notation. Okay, we can write very quickly nodal equations for nodal voltages. We can write, for example, we can put here Vx as auxiliary node, and then we can write Vx times all admittances connected to this node, R1, 1 over R2 plus SC1, minus neighboring node is V2, 1 over R2, and this is V3 over R1. And then we have a node 2, 1 over R2 plus SC2. And this is minus Vx 1 over R2, and this is equal to 0. Okay, and now it's very simple to solve it. From here we have what is Vx, this is V2, R1 plus R2 SC2, and this goes into the first equation. Very quickly we will solve it now, just to see what we get. V2, 1 plus R2 C2 times S 1 over R1 plus 1 over R2 plus SC1 minus V2 1 over R2 is equal to V3 over R1. Now we can multiply it. 1 over R1 plus 1 over R2 plus SC1 plus S R2 C2 1 over R1 plus S C2 plus S squared R2 C1 C2 minus 1 over R2 is equal to 1 over R1 times V3. And now we can delete 1 over R2 and minus 1 over R2. And then we can multiply everything by R1. And we will get V2 1 plus SR1 C1 plus SR2 C2 plus SR1 C2 plus S square R1 R2 C1 C2, which is equal to V3. And now we can try to calculate T23, which is equal to V2 over V3, and we will have 1 over S square R1 R2 C1 C2 plus S R1 C1 plus R1 C2 plus R2 C2 plus 1. And also what we always like to write in the form that there is unity before this highest potential in the denominator, then we can write S square plus S, which multiplies R1 C1 plus R1 C2 plus R2 C2 R1 R2 C1 C2 times S plus 1 over R1 R2 C1 C2. Okay. R1 R2 C1 C2. And then S squared plus omega, let's call it omega 0 over Q kappa S plus omega 0 square. And here must be omega 0 square times K. Let's call it K to 3. Okay, now we have noticed when we write transfer function of this circuit, V2 over V3, we very quickly come to this form like this, and then we can recognize the parameters like omega 0 square. If we compare this, then we will be able to write omega 0 square is 1 over R1 R2 C1 C2. Omega 0 over Q hat is equal to R1 C1 plus R1 C2 plus R2 C2 over this. From here you have omega 0 as 1 over square root R1 R2 C1 C2. Here you have Q hat as let's say like this. You can very quickly calculate it. And then you can also recognize that K to 3 is equal to 1. Okay, so now we recognize these 3 parameters of this network here. And we immediately can conclude that this network has low pass character. So this here is low pass character. Okay, and we see that the poles are in the a negative real axis. Now we would like to solve another example. Like this. If we now exchange these 2 points, 3 and 1, we will have the following. We will have the following network. Let's say it looks like this. Here is now C1, and R1 is going here down, and here we have R2, and then we have C2. V2, R1, C2. Okay, and now we have the following. We have the following network. This is node 1. This is still node 2 as before. Node 3 is now here. It is grounded, and we have ideal source. Here is auxiliary Vx. We have ideal source here, voltage source V1, and now we are going to find T 1, 2, which is V2 over V1. Again, we will use the same equations, but now we can use the equations from before, and we will see that these equations are indeed the same. So we can write Vx is 1 over R1 plus 1 over R2 plus SC1. This is the same. Minus V2 1 over R2. This is also the same. But now here, what is new is that we have V1 times SC1. This is the only difference. And for the second equation, we have again minus Vx 1 over R2 plus V2 1 over R2s plus SC2 is equal to 0. And now we have a x V2 1 plus S R2C2. Okay. And now it's very easy to see that all this here is the same, except this on the right side, which is V2 1 over R1 plus SC1, because 1 over R2 is deleted, plus SR2C2 1 over R1 plus SC2 plus S square R2 C1 C2. And this is equal to V1 minus SC1. And now all what we have to do is to multiply it by R1, and we have again the same left side, V2 1 plus S R1 C1 plus S R2 C2 plus S R1 C2 plus S square R1 R2 C1 C2, and this is equal to V1, or maybe in the different color, V1 times S R1 C1. Okay, so this is the difference. Here we have V3, and here we have V1 times S R1 C1. Everything else is the same. So finally, because we started from the same network, we just entered into the network from the different entering point. T2 T1 3, no, T1 2, just check. So T1 2 is equal to V1 V2 over V1. And we will have the following equation. S square R1 R2 C1 C2 plus S R1 C1 plus R1 C2 plus R2 C2 plus 1. And here we have S R1 C1, or we can write it in the form S square plus S R1 C1 R1 C2 R2 C2 plus, and here we have S1 over R2 C2. And this can be equated to the general form like this. Plus omega 0 square, and here we can have K1, 2 omega 0 over Q hat. Okay, what we can here notice, again, we have omega 0, which is the same. Omega 0 is the same, Q is the same, only small difference in the numerator. So here is this in the numerator and here is that in the numerator. Here is one very important thing missing, which multiplies S. And now we can say, aha, on the left side, we have low pass network. This is low pass character. The denominators are equal, but in the numerator, we have low pass network. Here we have bandpass network in the numerator. Okay, and where are the poles? On the low pass network, we have two real and negative poles on the real axis, and then we have two zeros in infinity. Here we have two negative and real poles, and we have only 1 0 in origin and 1 0 in infinity. Okay, so this is low pass and this is band pass character of the network. And here, of course, we can call this network bandpass network. But because this network is the same as the low pass network, they differ only in the numerators. And this is all what we wanted to say now here. We can also draw a universal network of those two. Let's see how this network could look like. It can have two inputs. Here is one resistor. Here is also one capacitor at the input. And here is another resistor and another capacitor. This is our RC network. Here can be grounded at this point, and this is output. R1, C1, R2, C2. And this is this was number 2. This was, let's say, number 1, and this was number, for example, node 3, and this can be node 0. Okay, this is RC network, which is, let's say, 2 input and 1 output network. This is universal network. How can we use input number 3? We can just connect here with voltage source wave 3, and this second input can be grounded. How can we use input number 1? Also very simple. We can ground input number 3 and put here voltage source at input number 1. And of course, in both cases, we can measure here voltage of the node 2. So this is V1. So this is our universal RC network with 2 inputs, and regarding the type of the network, we can choose one or another input, and we will always have the same poles and the same network parameters. So this was a small analysis. Okay. Now we repeat our signal flow graph from last time. Like this. For example, here in example of the class 1, just to repeat, and then we'll continue. In the class 1 function, we had need for the low pass and for the bandpass transfer function. Because if you look at the very simple signal flow graph, like this one here, then you can write T of S using Mason's rule is nothing else but T12 1 plus beta times T32 of S. And we have already seen that T12 has the form like N12 of S divided by D12 of S. T32, it has also the following form, N32 of S divided by D32 of S. And if we include it here, we can write N12 of S over D12 of S, 1 plus beta N32 of S over D32 of S. And now, if we want to continue to the next step, what we need? We need that D12 of S is equal to D32 of S, and we can put universal D of S of the passive network, and this is what we have just seen. This is always true if you use one single network. Regardless of the input point, you will have the denominators the same. So we can now write that this is equal to N12 of S over D of S plus 1 plus beta N32 of S over D of S. And now we can write it like D of S plus beta N32 of S, and here is 1 N12 of S in the numerator. And this is equal to D of S, which is numerator over denominator of S. Here, denominator of S is indeed D of S plus beta N32 of S. And then if we look at this here signal flow graph, so this is very important repeating, then now we'll continue very fast. If we look at this signal flow graph, we immediately see that D12 is here. T12 is here. And what is here also missing is minus beta, but it's okay. So numerator is here is also minus beta, but it doesn't matter much. Numerator is defining the character of the overall closed loop function, and denominator is here the function t32. This is in denominator. This is in the denominator, and this here is in numerator. This here. So the character of the overall transfer function is defined by this one. And the character of the position of the poles regarding this characteristic function is defined by this one in the feedback. So this was the basic repetition which we learned last time, and we see that very important condition is to have the same RC network, but this RC network can have two kind of transfer functions. So in the future, we will have to choose the correct networks. Otherwise, we can get nothing. Okay. So we have also seen that we have these two possibilities in the first class. Okay. Now this is what we have already all seen last time. Now we will continue with the class 3 because we have told that the class 1 and class 2 are just theoretical classes. And here we are still with the same signal flow graph, which has here minus beta. This has here T32. This has here T12. And this is output is 0.3. Midpoint is 0.2, and then you have this is a passive RC network, and then you have input number 1. Okay, we know that the transfer function is, we write it again, minus beta T12 1 plus, this plus is because it's negative feedback, T32, and this is N of S over D of S. Now, the question is, in the third possibility, how T32 looks like. So we saw in the first two cases that T32 was once it was low pass, another time it was high pass, but what is now in this case? In this case, we will see the following situation. One of the key points says that root loci on the negative real axis are left of the odd order of the characteristic point. The characteristic values are P1 and P2, so the root locus must be here. It's not good if it is here or there, then we will not have solution. So the root locus must be here, left. What does it mean? If you put 1 0 here, then it will not be here, it will be there, which we don't want. But the correct place to put zeros may be somewhere here. Now we are still on the left side of the first or odd order characteristic value, and these things are going out. Okay. So if you try now to calculate the position of the obtained poles, they can be obtained here in the complex plane. So it was very good for us that if you have zeros here, that the root locus will go away of negative real axis. This is what we wanted to have. So here is beta equal to 0 in these points. but here is beta is going to infinity, so the root locus finishes in the place of the zeros where there is infinity. Okay, so this is what we know from the last time. Okay, so we can now conclude that the third possibility is that the zeros are here somewhere conjugate complex, and this is good for us. So this is example, so they can all be here, and the transfer function t free to have the following form. Okay. Now the next question is how we can get the position of zeros here. How we can get it? So we need a special network. It's not enough to have simple ladder RC network like before. Okay. Before we continue, I can also here write d of s is 1 plus beta t free 2 of s, and d of s must be 0. It's the same like, so this is called characteristic equation. So it's 1 plus beta n free 2 of s over d of s, and this is then beta n free 2 of s over d of s is equal to -1. So this is form of characteristic equation. And you see immediately that zeros of n free 2 are those here. And zeros of d of s are those two poles here. So it starts from poles of the open loop network and finishes in the zeros of the open loop network, and beta is going from 0 to infinity. So just to repeat. Okay, now the question is how can we have these zeros here, which are complex conjugate like this? So we need some special network like this on the slide, and it's called bridged T network. Bridged T network can form almost zeros on the j omega axis, but not quite. There is some special condition which is called Fialkov-Gerst condition. It says that conjugate complex zeros are realizable, but it's limited in the right half plane up to p over m. M is equal to 2 because this is second order network. So p over m is p half. We will see it. Here we see it. So this network cannot have zeros up to here. So p half is the forbidden location for zeros, but on the left side, it's permissible location for zeros. This small epsilon says that they can also be more near to j omega axis, but the problem is in that case they need to have very large ratios of their values. For example, 1 million or 1 billion or so on, which is not very nice. If you have 1 ohm and 1 mega ohm and in the same network, it's not so very attractive network. So it's not, so to conclude, it's not possible to move this too much to j omega axis. Okay, but we also have twin T network, which has 1, 2, and 3 capacitors, and this is indeed the third order network. And then it has one complex conjugate poles and one complex conjugate zeros, and one real pole and another one real zero here. And then if you look at the possible place of this zeros, you can see that they can very easily be moved to the j omega axis, but also they can be on the j omega axis and can go even little bit more to the right, because m is equal to 3 and the P third is the forbidden area for the zero. So everything what we have to remember is that there are twin-tail and bridge-tail networks. Twin-tail network is of the third order and bridge-tail is of the second order. Okay. Now it can be also said that it's there exists possibility that these two zeros and poles can be deleted if they are same. If you use special values of these here elements, if you use special values like we will see, then there is possibility that this appears like a second order network, because this is everything what is left, and it looks like second order network, although it has three capacitors. Okay. This is this example where P and P0 and Z0 are deleted. So they can readily be designed to cancel. Okay. Because of this Fialkov-Gersh condition, this network can be used to realize even the zeros here on J omega axis, like I plot now here. So for beta infinity, these zeros can be here on J omega axis. Okay. Most class 3 filters use bridge T because twin T is rather complicated. It's big. It has more elements, and we will see that although, as we see now, the bridge T is more simple than twin T, and the bridge T cannot have zeros on J omega axis. This will be overcome by something else later. So here is the bandpass. Let's say it's a conjugate complex poles in the. It's not bandpass. It altogether is bandpass filter. If you look at 1, 2, but in the feedback, this is T3, 2, and this is T1, 2. So as we know, T1, 2 is determining the N of S. So this is the character of the whole filter, and T3, 2 is feedback. So in feedback, you can make complex conjugate poles. Okay, here is also. And if we try to calculate the values, so you can try to do it by yourself, you will have the following equations. So finally, omega P is equal to omega 0. We remember what is omega 0. This is 1 over R1, R2, C1, C2. So omega 0 is then equal to omega P. So we can say that omega P is now very stable. It doesn't depend of the gain beta. So this is something what we want. And what is the QP? The QP is equal to QZ, and this is the position of those two guys. So if they are closer to J omega axis, like here, and then we can obtain large QP, which are of course larger than 1/2. But let's say we are using open loop gain. Now we see the circuit. Probably you have already seen such a circuit. This is going here to minus, and this is another form which has, for example, here you have bandpass T1, 2, and here you have high pass T1, 2. So that's why this is high pass filter. That's why this is bandpass filter. You just have to look at the path of the signal. So as you see, A is equal to beta, and it's going to infinity. So this beta here is indeed the gain of our open loop amplifier. So this comes to near, because beta is A, it's almost infinity. It's not infinity, it's 1 million maybe, but the poles are very near to the zero. So now it's the problem, how can we get poles here? This is not possible if we cannot move these zeros more to here. So this is the same problem that we were discussing here. So as you see, to do it, you must have very big ratio of the values of this RC network. Okay, so this is the low pass and this is the band pass. Okay, T12 and T32 are here. So we say again, this is smaller than 1/2 and this is much higher than 1/2 because it's for beta is going to infinity. So we have poles here. So this is the class 3 network. What are the advantages? Omega 0 or omega p is independent of the gain. Root locus are circular. And we can design low pass, high pass, and band pass filters. What are the disadvantages? The higher Q. For the high Q, we need the high spread of RC components, and frequency reject or bandstop filters are not possible. So this section will not be usable to design elliptic filters because as we said before, they need finite values of zeros. This was all for the negative feedback. This here is example of negative feedback. But if we make, so this was negative. How can we have positive feedback? We can have it like if we put plus here, and that's it. So this is the positive feedback. And then our equation has here minus. So here is minus. So this is the only difference. Here is plus. So this is what we get here. And we also can use, as you see, signal flow graphs, and it's easy. So this is also very important condition which we have derived today in the beginning. So that's why I wanted to emphasize this, and then to emphasize how you can derive it. Okay. Now the characteristic equation has here plus. This also I can plot here. And the key point is that now I can start from the beginning. So if you have by positive feedback P1 and P2 here, you can also have 1, 0 here. So then the root locus will start left of the even number of the critical frequencies. So this is 1, this is 2, left of the 2 is here. So it must start here, and then it will go up. No, just a moment. It can go like this. It can finish here. But here, if there is another 0, it can stop there. So the root locus looks like this. This goes here to infinity, and from infinity goes to here, and here stops. So this is the root locus of the positive feedback, and it's on the left of the even number. So this is 1, 2, so left of the 2. So it's here. And goes to the right of the rightmost critical. This is the rightmost, and goes to the right, goes here. So this is how it can look like. And this is characteristic equation. Beta n free 2 over d hat is equal plus 1. So it again starts in the characteristic zeros of d of s and finish is in zeros of n free 2 of s. Okay, So now we immediately see what is the transfer function of this T32, how it should look like. So we know that this is defined by T32 of S. So because here is N32, T is always the same. So T32 of S, which has 1 0 here in infinity in origin and 1 0 in 1 0 in infinity, it can have the form like this. Here is K32 omega 0 over Q hat times S. Okay, so T32 is of the bandpass character. This is what is very fast seen here, and that's why we have 1 0 in the origin and 1 in infinity. So what we will need, so here are all possible positions. For we have used one which is green, the green one, and the green one has 1 0 in infinity. This is Z1, and Z1 prime can be here or in infinity. Here is how it looks like. And as you see, T32 is bandpass function. So we concluded properly. Okay. So because of positive feedback, here we will have bandpass function, and this flow of the signal will determine the look of the transfer function at all. So the whole function. Okay, so if you remember, we started in the beginning of our lecture today with such a general RC network which has two inputs. In one input is V1, in second input is the output of this operational amplifier. You must remember that output of the amplifier here is also nothing else but voltage source. So this is V3 voltage source. So everything is good. Here are possibilities of how to make bandpass networks. So you remember something like this. Or, so this is bandpass, or it can be something like this. Of course, here we can exchange R's and C's and have this. So these are all bandpass networks, and of course, they are in the feedback, like here, like here. So these are all possibilities of T32. Okay. Now is another question open, but before we continue, we will make a short pause. And today we'll probably have a little bit longer to finish what is prepared for today, but we will make some breaks. Now it's 10-minute break, and we'll continue after 10 minutes.
Okay.
Hello. Now we continue where we stopped before pauses. So we continue with one passive network, which is called grounded free pole network. This is grounded free pole network. It has free poles and it has some special characteristic that if you calculate transfer function V2 over V1, and of course V3 is equal to 0, then if you exchange input terminal and ground, you have to calculate V2 over V3 when V1 is 0. So now we have changed these two nodes and we can very easily show, this is called complementary transfer functions, that T32 is 1 minus T12. So this is also possible to prove, but we will not show it here. It's very simple. Okay. This is one example. If we have such a special network, as if you remember, I told you will have a special values. For example, if you choose C and C, this guy here must be 2C, and then this pole and 0, which are real, will reduce, and you will have second order transfer function like this. Or if you choose R and R, then this guy must be R half. So these are the special values. If you introduce special values in such a network, then you have band reject network, and which has zeros on the j omega axis, and because of this, the 0 is here, is going up to 0. So this is band reject transfer function. Next, if you try to calculate 1 minus this band reject, you will obtain band pass. So this is band pass. So from this network, you can have both band pass and band reject. And what we will need here is the band pass. As you see, we were here plotting 3 examples of bandpass, and here is another one, 4th example of bandpass. This is this network here. So this is bandpass if you change 1 and 3. Okay. So it's also good to say at this point that if some network has bridged T, and if you exchange 1 and 3, then it will become like ladder. So bridge T becomes ladder if you exchange input and ground or nodes. Oh, and vice versa, of course, if you have ladder network and if you exchange 1 and 3, you again obtain bridge T network. And this is finally our circuit. So here in the feedback is T32. So what you will see, it's possible to have band pass network. And here, if you go from here, it's possible to obtain band reject. So here now we have the first example of band reject network. Here is bandpass so this is T12. Okay. Finally, this class 4 is capable to realize the final transfer function, which is band rejection network. So this is the first time that we are able to obtain band rejection network, but with this QP, which is larger than 1/2, because here it was smaller than 1/2, as you remember. Okay, so our twin T network was very useful for obtaining band reject network. Okay, now we see T32 is bandpass and T12 is what it is. Here is how we can calculate the closed loop poles from the open loop poles and the gain beta. So these are the results. Again, what we like is that omega p is independent of the beta, but here you see another thing. If this in the denominator equals to 0, then you can obtain Q, which is infinity. So beta must be smaller than some beta critical, not to obtain Q to be infinity, because in that case the filter will become unstable. But as you see, the Q is again larger than 1/2. But using this method, here is the minus. Before we didn't have any minus, if you remember. Okay. So this is a realization. What is also here important to notice, here we have one symbol of the gain plus beta, but this is realized by this non-inverting amplifier. So these two things are totally the same, so you can immediately see how we realize this plus beta. Another important thing is that every class 4 network can be regarded as single feedback or dual feedback. So if we go back, this is single feedback. This is here single feedback, because there is only one feedback. And there is here one feedback, but we can regard this as a second feedback. So here are below are two feedbacks. So the second feedback network is resistive network, and it's okay. So every class 4 network, because it has this positive gain element, can be regarded as single feedback or double feedback. Here you see two feedbacks. It's very simple. It's not big deal. Okay. Here are examples. If you want to have bandpass biquad, you probably remember this. You probably saw it. The signal is going here. In the feedback is bandpass, and in the forward is also bandpass. So this is altogether bandpass biquad, but of the class 4, because the signal is going to plus. Okay. This is calculation of the parameters. This is what we know already. Advantages at that omega is independent of the gain. Q is needing a very, very low gain. So for example, if you have gain, which is beta must be lower, higher or equal to 1, because beta is 1 plus RF over R ground. If you use this, this is what we know. So this is R ground and R feedback. So this can be replaced by beta plus, and beta is, because of this equation, beta is larger or equal to unity. And we will see that we need beta between 1 and 2, maybe, because this is beta critical, here is 2. So beta does not need to be too large. What is this one? This one stage is because beta must be remain below critical to prevent oscillation. So this is like this, because this part here then can be 0, and you have division by 0, you have infinity, and that's not good. Okay. Here is also another example. What is the difference as before? Look, if you look at this here, RC network, I can use some other notation. So RC network is here on the minus. And here, RC net, not RC, R network, so voltage divider, not RC. Voltage divider, pure resistor network is here on the plus. You see? So here it's on the minus. Here is on the minus. Here is on the plus. Input of the operational amplifier. Okay, so if we consider this then we can also make new analysis. So signal flow graph will have another feedback. So this was our normal till now, and this is new. And then we can say that transfer function can be obtained in this form. So this is obvious from the signal flow graph. You put it here, you make A going to infinity, and then you have this here, and then with T1, 2, and T3 to here, you obtain this. Okay, this is overall transfer function. This is something that you can also use when you calculate. Now the question is how this additional alpha will make the poles of this T of S. So this now we have n 3, 2 minus alpha d equal to 0 from this here. And then you can rewrite it. So that's it here. You can rewrite it in this form. So now you have new characteristic equation, which is dependent on alpha, and d is now in the numerator and n is in denominator. So open loop zeros are end points of the root locus with respect to alpha, and open loop poles are starting points of the root locus with respect to alpha. And alpha is this additional guy, this additional resistive guy. So this is what we have till now, and this is addition. Now we'll see how this addition works. If you remember before, it was opposite. It was n 3, 2 in the numerator and d in denominator. And it was here -1. But here we have +1 and d in numerator and n 3, 2 in denominator. It's inverting. And now we can conclude, looking at these two characteristic equations, that by adding positive feedback alpha to negative feedback beta, the role of open loop poles and zeros for the corresponding root loci with respect to alpha and negative beta feedback are exchanged. Here it is, but this doesn't help us. So if we add this red one, it doesn't help us. It's the root locus is only here. Here also doesn't help us because alpha is only on the negative real or positive real axis. It doesn't help us. But here, if we finish with beta infinity and we add two resistors, which are represented by this alpha, then we can move additionally poles to be more near to j omega axis. Okay? We can say that the red lines are complementary to the blue root locus lines. Okay? So we can say the additional positive feedback is very useful to overcome high Q limitations of class 3 networks. That's finally a good and well-known filter. So if you remember, I was telling you before that R4 to R1 or C1 to C2 must be 1 million if you want to have big pole Qs. But now if you add these two guys, then you don't need to do it. You can have equal capacitors here and equal resistors here, and you can get whatever Q you want because then it goes here more near. So the red line helps. These two guys helps because of they are performing alpha. Okay, so this is the signal flow graph of the double feedback class 3 bandpass filter. Here you can see immediately that QZ, which was problematic, is now increased by this factor because of alpha. And everything else is the same. This is as before. Okay. Now we can say that design of that so far we have learned how to design low pass, high pass, band pass, and band reject was only possible to use class 4. That means positive feedback. We have not discussed all pass filters, and the problem is with design of elliptic filters, because we need band reject with class 4 circuit using very cumbersome twin T. Is there a better way? The better way is to use differential input. Till now we had only single input, but single or double feedback. But now we can also apply differential input, and then you will see that we have more possibilities. This is very simple from circuit theory, that if you want to obtain polynomial with arbitrary roots and to have a possibility to obtain a position of P of S or roots of P of S anywhere in the plane, then you must make subtraction. This minus is very important, of two impedances, for example. Or you can make subtraction of two transfer functions, and it's even easier because the limitations on the roots of Z of S are more stringent than those of transfer function. T of S is RC transfer function, and then how we make this minus? We go with two signal paths from the input, and then we have subtraction here because of plus and minus A. So this is what we can do. Here is the whole network. So this here is transfer function in the input. This is feedback. You have a biquad differential input, which can then realize zeros anywhere in the S-plane. So you doesn't need anymore to have twin T. You can use simple bridge T network. And here is our network finally. So if you add these two here to have two inputs, like here, then you have this in the numerator, and you will be able to have zeros on the anywhere on the S-plane as complex conjugate. For example, you can build all-pass filter like this. So you see it has here two inputs. It has two feedbacks. So you have everything here on this signal flow graph, and you can obtain all-pass filter. Okay. This is band rejection biquad. This is also a very useful circuit. Again, you have class 3, and you have two inputs and two feedbacks. Okay. Here is summary of our way of obtaining conjugate complex poles regarding different classes. Here is how the complex conjugate poles, how they go out of the real axis for all four classes. Here is another example of all-pass network. Here are parts of it, so you can try to calculate it at home. This is a condition for having all-pass. This is condition for having notch filters. Here are some examples of all-pass and notch biquads. We start with all-pass, so you see plenty of them. Here and here and here, and below are notch filters. There are really many filters of them. You see how many they are. So they are all from the paper of Norbert Fliege. And Fliege means fly. Fly is the thing which is flying, and in German it's Fliege. So Norbert the Fly drew all these examples. So this was our classification story. But now we will continue with another slides today. These are examples of calculation of electrical filters. So this second part, which starts now immediately, we will finish to the end. It's not so complicated. We will here learn how to calculate examples of electrical filters, which can you expect to have in your exam. So now this is also preparation for the examination. This is first example. Of course, all these slides you have here in your repository of the data. For the second order Chebyshev filter, this is example number 1. For the second order Chebyshev filter, with maximum ripple in the passband of 2.5 decibel. 2.5 decibel is something what we know already that it doesn't exist in the tables, so we have to calculate. We have to use our equations that we have learned so far. So you must design filter or transfer function and then filter. You must then normalize it to cutoff frequency of 100 Hz and write expressions for amplitude and phase frequency characteristics. For the cutoff frequency, we choose the highest frequency at which the amplitude frequency response takes the value of the minimum in the passband. Sketch the amplitude frequency and phase frequency responses and mark the characteristic points. To determine the amount of phase and amplitude in decibel signal at the output of the filter if the signal frequency is given by 100 Hz. So if you put the signal, determine the amount of phase and amplitude at the output of the filter. Okay, so this is one example of the exam question. Of course, you can design a filter of Chebyshev using Chebyshev transfer function. And then you know already from before, which we have learned, that its value at 0 is 1 over 1 plus epsilon. And if the order is even, and is equal to 1 if the order is odd. So in our example, we have even order 2, and it is given by this. Of course, on the picture you can see it. So for the odd order, we have gain at 0 here. For the even order, we have gain at 0 here. So this is our Chebyshev characteristic. Now, in our example, its epsilon is equal to 0.882201. If you put it in this simple equation, or if you try to calculate K, then you can use another equation like this. So you can obtain K if you introduce DC. So this is DC gain K. Okay. We know these equations from before. If you know this is second order, you know epsilon, which is obtained from here, from this guy here, or from here. Then you have the possibility to calculate poles. Poles are here, they are conjugate complex. You can put them back in your H of S. You can calculate from real and imaginary parts of poles. You can calculate omega p or QP, which is something what we already know. This is general form of the low pass filter. And then it's also plot here. This is something already what we have done. You can look at the slides by yourself. And then you see here that if the QP is larger, this is here, when sigma, which is real part, is smaller. So if the pole's going to be near to imaginary axis, you will have larger QP. Sigma is notation for real part of poles. Omega tilde denotes imaginary part of poles. And omega without tilde is then the distance of the poles from infinity. This is what we already know. Okay, now here are the values in our example. Here is omega, it's QP, and you must introduce it here, and finally at the end you add the K. So K is obtainable in two ways. Everything is the correct, and here finally you have the H of S in the normalized form. So this is second order low pass Chebyshev filter in the normalized form of 2.5 decibels. Usually you can read it from tables, but this here is just to show that we use for real part we use sigma, for imaginary part we use omega tilde, we use QP, and we use omega p as notations. So this here example is for Butterworth, but okay. In the book, which I have already shown you, this is electrical filters. There are tables from 0.1, 0.2, 0.5, 1, 2, and 3 decibels. So there is no zeros and poles for 2.5 decibel ripple. So you will have to calculate it. Now we want to make denormalization to 100 Hertz. So if this denormalization is properly done, then you use the following frequency transformation. We were talking already about frequency transformation. S over omega g. Omega g is given as to be 100. And then you go into your normalized transfer function. Instead of S, you put this, like this. And then you can try to calculate frequency response. It's calculated by substitution S instead of Sj omega, and you put it into H of S, and you obtain this, and you obtained this, the following step. And then amplitude frequency response looks like this. And if you make logarithmic measure, then you must include 20 logarithm of absolute H of S. Or if you calculate the phase, it's arcus tangens imaginary over real, and that's it. Now, very important notice, which I want to show you. It's always very useful to calculate. So you start off H of S, put S equal to J omega, and then you obtain H of J omega, and you put some omega equal to something, omega g, or let's say omega 1, and then you have H of J omega 1. For example, we have here H of J 6 to 8, which is 2 pi 100, like this. So we have chosen the same value, so we have omega over omega g, or omega over omega 1 to be 1. And then you just have to introduce here 1, so it's simple to be calculated. That's why we have used the special value of omega. And then what is now important, which I wanted to tell you, then the question is where this H of J of omega 1, where it is situated. So it's very useful to plot it in the S-plane, because you see that it's in the third quadrant. Because this guy here, if you have only positive values, it will be in the first. So you don't know, is it in the first or in the third quadrant? Therefore, it's very, very useful to plot the position of H of J in order that you have a correct value of the phase. Otherwise, you will not know the phase. So my advice is whenever you have input signal given as sinusoidal stationary signal, like this one here. So this is sinusoidal signal, and then you calculate it using phasors or complex numbers, then you must plot your phasors or complex numbers in the S-plane to see the correct position. If you calculate arcus tangens of minus 0.7097 over minus 0.2428, then this you will have the same as arcus tangens of plus 0.7097 over 0.2428. So they will give you the same value, so you will not know if you are here or you are here. So this is in MATLAB function atan. But you have in MATLAB atan 2, then you have real and imaginary parts. This is here imaginary over real. Split, then here you know the position of your phase. Okay. So here, when you calculate correctly, you obtain this gain. If you apply 20 logarithms, you have minus 2.5 dBs, and you have here the following phase. Output signal is here. This is the plot of the signal. This is plot of the phase of the signal. And that's it. Now we continue with the second example. Second example is very important for us because here we finally learn how to calculate one filter from the beginning to the end. So in this example, we have to use biquad in the figure. We see this is class 4. This is low pass. You see it immediately. So bandpass is in the feedback. Here is bandpass in the feedback. So it's class 4. The signal comes here to plus. And here is low pass in the forward path. So you immediately recognize this is class 4 low pass filter. And it's also very known as Sallen-Key filter. Sallen-Key wrote this paper in 1955. So very, very long time ago. But they were not using op-amps, they were using vacuum tubes. Okay. Now we want to see how this transfer function of this circuit looks like, and we immediately see that it's too complicated. Now we can simplify this circuit. We can simplify this part here and this part here. This part here we already know this can be represented by beta. This is what we were already doing. But this part here, the first part, is voltage divider, and this voltage divider can also be replaced by Thevenin. So here we assume that R1 is R11 and R12 in parallel. Okay. So this is a Thevenin equivalent circuit at the input. It can be replaced by this simpler version. V2 is then alpha V1, and alpha is voltage division ratio. R1 is R11 and R12 in parallel. So we can also calculate R11 and R12 back if we know R1 and alpha. So this is also useful to say now. Amplifier, this is something what I have already draw you today. So this is non-inverting amplifier with two resistors in negative feedback, and this is positive beta, which is larger than unity. So our filter circuit now looks much much simpler. As you see, we don't have any more so many data, and here the transfer function is also more simple. Okay, so we expect it will be simpler for us to solve it. If we try to equate with this general form like we did already, then we'll obtain the equations for omega p, for qp, for k. And of course, with these abbreviations, alpha, beta, and R1, this is something what we have already used. Now we have example of Butterworth filter, and this Butterworth filter have three conditions: K, QP, and omega p. So these three parameters of these three conditions are here. Now we have 7 elements, and then we have 4 degrees of freedom. Why 4 degrees? Because we have seen so far, not here, but here, that we have 7 elements: R11, R12, R2, C2, RG, RF, C1, and C2. These are 7 passive elements which have to be calculated. But we have 3 conditions which are given by omega p, qp, and k. So 7 minus 3 is 4 degrees of freedom. 4 of the elements should be chosen to finish our circuit calculation. If we choose equal resistors and if we choose equal capacitors, we have used only 2 degrees of freedom out of 4. And if we put them into our design equations here, which are here, so if we put them here, R1 equal to R2, C1 equal to C2, then what we get is much simpler form of the design equations. We have now more simple design equations. You see, everything is getting more and more simple. Now, this is example of calculation. If we choose C equal to 1, this is the 3rd degree of freedom. If we choose RG equal to 1, this is 4th degree of freedom. Omega p is given, QP is given, K is given. We calculate R, we calculate beta, and from beta we calculate RF. And then at the end from K we calculate alpha. And here from alpha and R1 we calculate R11 and R12 at the end, and we know all these. So finally we have all the normalized elements. You see the process of calculation of normalized elements, how is this simple. So you must recognize step-by-step procedure of calculating this filter. Okay. So this is our filter. Here are normalized elements. They are on its place. So as you see, we have here transfer function which is normalized to unity. So this is -3 dB at the frequency of unity radians. So with this normalized filter you have it. Okay, now in the next step we want to denormalize elements to obtain a real filter which you can buy elements in the store and then you can solder it or put it on the breadboard. Here are equations for denormalization. Usually you have 2 parameters for denormalization. This is omega 0, which is called denormalization by frequency, and R0, which is called denormalization by impedance. So here is how you can perform it, or you can use this. So this is all equivalent. Okay, what we use for omega 0, we usually use cutoff frequency. What we use for R0, we usually use resistance of the network. And now, from a special wish of the value of R0, we wish to use capacitors of 100 nanofarad. Therefore, we need to adjust R0 to obtain 100 nanofarad. Okay? So, R0 is 1.59 kilo ohm, and C0 is then, if you use R0, because you can choose whatever R0 is or whatever omega 0. Omega 0 we have chosen as a cutoff frequency. We will see later. And R0 can be whatever, but we wanted to buy C0 100 nanofarad in the store, and this is because these are nice capacitors, and we build discrete component filter. We don't build integrated circuit filter. We build a discrete component filter. Then we can use capacitors of some very nice value. And if we make denormalization, we obtain the following elements here. Here are the way how you do it. For example, you see this is 2.5 kilo ohm, 4.3 kilo ohm, and so on. You have 100 nanofarad and so on. And then if you put it into the circuit, you obtain the following transfer function. So here is the cutoff frequency of 100 Hertz. So this is the normalized amplitude frequency characteristic. Okay, so this is the filter. You see, you can buy these nanofarads and kilo ohms in the store, and you have cutoff of 100 Hertz. Usually, what we choose for R0, if you want to make some filter for telecom, then you will have to use R0 of 600 ohms because it is the resistance of the telecom provider. For example, A1. Okay. Now there is next question. What will happen if you increase impedance 10 times? For example, if you use R0 larger 10 times, what will happen? So you see that tau is R times C. If you increase R 10 times and you decrease capacitors 10 times, the product will be 10R times C over 10. The product will be the same because these two go away. So if you increase all impedances, by 10, what means increasing capacitor by 10? So admittance of the capacitance is 1 over omega C. So to increase it 10 times, you must decrease 10 times the value of capacitance. So by resistor, it's simple. So if you increase resistor by 10 times, you increase resistor by 10 times. But capacitors, you must decrease 10 times to increase its impedance by, or let's say, reactance by 10 times. Okay, but the most important thing is that RC product is staying the same. So all capacitors are 10 times smaller and resistances are 10 times larger, but amplitude frequency characteristic of the filter has remained the same. RC constants didn't change. So here is our same RC constant, but what we have here? We have here smaller values of capacitances and larger values of resistances. So, but the transfer function is the same. The transfer function is the same. So this is the transfer function. So this circuit here and this circuit here have the same transfer function, but the overall impedance of the circuit has increased. So this is not something so very problematic. Now we have the third example. I would like to make another pause of 10 minutes and then to finish with the third example because it's very important. It will be another maybe 15 or 20 minutes long, but let's make a pause of 10 minutes.
Okay.
We continue with our third part today. So all what we have to do is to solve the example number 3. Probably you will recognize what we were already deriving. This is something what is called low pass to band pass transformation, and it is done by applying the following frequency transformation. So omega 0 is the center or central frequency, or B, and B is the band width of the filter. How it works? This is something what we have also already seen, but just to repeat, if you have normalized low pass transfer function, we start from normalized and we finish with denormalized transfer function. So, for example, if you have, let's say second order, can be anything else, but let's say second order example. Second order low pass prototype filter is like this. This is 1, this is unity, cutoff frequency. Here is gain of 0 dB, for example. This is A of omega. This is minus 3 dB. And this goes here, just a moment. In that case, it will look like this. This will go to minus infinity. How does look bandpass resultant filter? This is omega 0. This here is when you go to 0 and to minus 3. A of omega. This is B, and this is omega 0. Now, if we see that this here is Butterworth, the bandpass filter here is also maximally like Butterworth, maximally without ripple, maximally flat. So this here is maximally flat, this here is maximally flat, here is minus 3 dB, this point here is defined by B. So here you have omega low and omega high frequencies, which are equal if you subtract omega high minus omega L, you will obtain bandwidth. Also, what is important to notice as a consequence of this low pass to band pass transformation, you will have the following, that omega 0 is geometrical mean of omega L times omega high. So this is band pass and this is low pass. Okay. So now, when we know what we will apply, this is low pass to band pass transformation, we can go to proceed with our example. There are equations which can be derived from these two, and they will give us the values of omega L and omega high. So this is also something what we have to calculate. Okay, so this example tells us to calculate the transfer function of the fourth order bandpass filter with Butterworth specifications with bandwidth of 1 kHz, FG and FD. So we use FG as F high, FD as F low, but we can also write that omega H is 2 pi FH and omega low is 2 pi F low. So this is the values. Okay, so central frequency is F0, omega 0 is 2 pi F0. So it is given B. B can be also multiplied by 2 pi. So B is equal to 1 kilohertz. But this is B, which is F high minus F low. And this is, let's say, B prime can be expressed by B times 2 pi, or just without, just to see that these two guys are not the same. Okay, so let's call this BF, like not B omega, but like BF. Okay, now we have to calculate frequencies FL and FH, and then we have to answer in which relationships are these cutoff frequencies with the central frequency. So this is the relationship, or we can write also F0 is FL times FH square root. Draw layout of zeros and poles in the complex S-plane. Determine expressions for the amplitude frequency and the phase frequency responses. Calculate the parameters of the two biquads that realize a fourth order transfer function in cascade, namely the gain, Q-factor poles, and frequency of poles. So this final task I will also here draw. Indeed, we will see, because this here is fourth order, and we started from the second order, and the order is doubled. We will see that it is possible to realize fourth order as cascade of second order biquads that the overall filter is of fourth order. This is bandpass. This is also bandpass, but second order. Okay. So how does look these two second order bandpass transfer function? This is called cascade. It looks like the following. Here is one. And here is another one. So if you have two second order in cascade, then you have these two red, and the resulting filter is the blue line here. What those two red have? They have omega 01, omega 02, which are different from omega L and omega H, and also they must have some Q01 and Q02, and of course K01 and K02. So we have K01, Q01, omega 01, K02, Q02, omega 02. So this is for the last part of our example. Okay, now the question is first how we have to calculate this fourth order function, and then in the next step we can realize them as a cascade of two second orders. So this is our third example. Okay. Because it's given for us to calculate the second order Butterworth prototype, but before I continue, I will say another thing. So if we have, for example, Chebyshev like this, then the bandpass will look the same. So the look of the characteristic is preserved. Okay, so that's it. Okay. So the normalized poles are here. We recognize them as poles of Butterworth transfer function. They also can be found in some books, in some tables, so we can use these data here, which are very known. Poles S1 and S2 are complex conjugate pair, therefore we group them, and then J will vanish. This is what we are doing now. J will vanish, and then we have this final low-pass transfer function, which is our starting point, and this is indeed the second order Butterworth, like here. Okay. Now we have to find which are omega of this low-pass prototype, Q of this low-pass prototype, and K. Here they are. So we start our design from the second order Butterworth low-pass prototype filter. Okay. And we must have the fourth order bandpass filter with the bandwidth B and central frequency omega 0. We start from here. We apply our transformation, which is here. You know it. If you put it here in this normalized low-pass prototype, you will have this. Okay. And then you will have to calculate it, and you see that you obtain the fourth order transfer function. Here are the coefficients which multiply s to the 4, s to the 3 power, s to the 2, s to the 1, and s to the 0. And then if you introduce the values, you obtain this transfer function. This is the normalized transfer function of the final fourth order bandpass filter And as you see, you have 10 to the power of 19, 10 to the power of 13, and so on, because this is a real transfer function with denormalized elements. If you want to find frequency response, you have to include S equal to j omega, and then you have the following. And then you have the amplitude frequency and phase frequency characteristics. Okay. So then we have the following transfer function or characteristics. From this transfer function, you have the following two characteristics, which is amplitude frequency and phase frequency. You can plot them using MATLAB. Here you see that we have started from F0 is 10 kilohertz. This is correct. This is central frequency. And then you see it's a bandwidth of like we started from 1 kilohertz. Okay. Now in the next step, we want to find these two guys here. So we must equate our transfer function, which is given here, this one, with this one. So if we equate them and we try to calculate these red parameters, we will find that Q01 is equal to Q02 is equal to Q. And this is very simplifying thing. That means that those two characteristics are with the same bandwidth or with the same Q. And they have omega 0 1 over omega 0 equal to omega 0 over omega 02. Or we can say that omega 01 times omega 02 is again omega 0 squared. So this is called geometrical mean because omega 0 is square root of omega 01 times omega 02. This is geometrical mean. Okay. So here, after some calculations, we have derived something what is called Geffy equations. These Geffy equations are well known. From then you can calculate these here and these here using these two equations. But what is left is K01 and K02. This is also very simple to obtain. If you compare the numerators, then you see that K1 times K2 must be this. Here are omega 01 and omega 02, and K and Q is 14. Okay, so we choose K01 equal to 1 and then K02 equal to 2.0025. So this is the way how we optimize for maximum dynamic range. Why we do it? Because if you have two biquads in cascade, and then you have K01 equal to 1 and K02 equal to 2 point whatever, 2.0025. Then if you put here maximum voltage of 1 volt, then here you will also have maximum 1 volt, and here you will also have maximum 1 volt. So this is the reason why we choose the first one equal to unity and the second one equal to product of the K1 times K2. Okay, now this is written here. Now we can finally calculate the poles and zeros and we can plot them. Here are equations for poles and zeros. You recognize these equations. These are very simple. And you can use the MATLAB function, which is called PZ plot, pole zero plot. So if you input the coefficients which you have calculated so far, these A0, A1, A2, A3, they are given here. They are given here. This is A0, this is A1, A0, A1, A2, A3, okay? Okay, and then you have the possibility to pole zero plot. If there is need to calculate those two, omega L and omega H, which I said this is Fg and Fd. G means up and D means low. Then you can use this equation. This is equation also easy to be derived. You can look in the books. And we have the following two values. And if you check back, you obtain B as 1 kilohertz. You can check also if you multiply this Fg and Fd or Fh of L or Fl and find square root, you will find F0 10 kilohertz, which we started from, and we can also conclude that F0 is geometrical mean of these two frequencies. Only in the special case it can be also arithmetical mean, but it's not so big deal because if you have the following very nice values, then you will have the arithmetic mean also. So you have to round. So 10,512 can be 10,500 and 9,500. So this is it. Okay, so this was our example of calculation of the bandpass filter and to be realized as two Biquad blocks of the bandpass character in the cascade. And this was our last example for today. Next time we will say few words about sensitivity and then we will finish with switch capacitor filters. But for today we have finished. If you have some questions, please ask now or send later some email.
Excuse me, I have some questions regarding the work for.
Okay.
I already asked you by email, but for my transfer function, I can't put it in the form you gave on the paper.
You mean for the homework?
Yes.
Okay. So then you will ask me by email. Okay. But some more questions about lectures. This is what I want to ask.
No question about the lectures for me too.
Okay, then probably it's clear. If it is not clear, then you can consult some books, so which I gave you. And then if you then also don't understand, then you can ask me, but prepare with the books so that you can have a good question. So for the next time, as I told, we will learn about sensitivities of active filters, which is very important topic. And then another very important topic, which we will finish with, is the switch capacitor filters. So next time it will be very interesting. So I suggest you to come to meeting, and then you ask, of course, if you have some questions. But till then, I will tell you, have a good weekend, and we'll see us next time. Bye bye.
Bye. Have a good day.
Bye.